This video is going to show you how to integrate using Monte Carlo methods. So to start with, here we have a velocity plot. So this is velocity versus time. The units of time are seconds. The units of velocity are meters per second. And this velocity, if you look at this, it looks about like somebody who just is learning how to drive a stick shift for the first time or something, a manual transmission, but going up and down fast and slowing down again. But the actual function for this is sine t times cosine 2t plus 1. So that's what this function is. And what we want to do is we want to find the area under the curve. But I don't want to I want to limit it to just a given section here. So what I want to do is actually want to find the area under the curve from about 1 second over to 7 seconds. All right, and so now if you look at this, come over to, try this again here. So from about 1 second, and I'm not sure if I quite have that ideally there, but about 1 second to 7 seconds. That's the area that we want to find. And I'm actually going to go a little bit above the maximum here. So if you look at this, okay, so we're going from so I had to wait for the computer to catch up there, but we're going from 1 second down here to 7 seconds. And notice here that this function is topping off right here at looks like 2. And so I'm actually going to run the area all the way up slightly above that. So I have a little bit of space above that. It's best when you do this Monte Carlo method to leave at least a little bit of space. So I'm going to run the velocity, allow that to go all the way up to 2.2. All right, so if we wanted to calculate the entire area of this rectangle, this entire rectangle, okay, so I want to get this entire area of the rectangle. Well, that is going to be the time, which is 7 minus 1, so it's 6 seconds. So the base of the rectangle would be 6 seconds. And the height is, as I already said, is going to be 2.2 meters per second. And so if you calculate that, you end up getting 13.2 meters. Okay, so the area of the rectangle is 13.2 meters. But now we want to find the area underneath the curve. And so what we're doing is we're saying everything underneath of this waveform is the area underneath the curve, including this area right here, right? This little bit of area right there is also under the curve. And so we want to find all the area in green. That's the area underneath the curve. And so we would like to throw darts at this rectangle. So I want to just kind of come in here and start throwing darts. And everywhere within this rectangle. And the idea is that if I throw them and make an even pattern, and then I calculate the percentage of darts that hit underneath here, which we'll call hits. So these will be hits. All right, anything below the curve we'll call a hit, and anything above the curve will be a miss. And so then we can take the ratio of hits to misses, right? Or hits to total darts. So if we look at the total amount of darts, and so we take the total area of the rectangle, right? So we take the total area of the rectangle, which is 13.2, and multiply that times the hits divided by the total darts. All right, so let's just say, for instance, that we used 100 darts total, and 50 of those fell below. Just as an example, say 50 of them fell below the line, then that would be 50%. And so you multiply 50% times your 13.2, and that'll give you 6.6 meters, right? 50% would be 6.6 meters. Again, this is just an example to illustrate this, but so by taking hits divided by total darts or total attempts, we're effectively getting a percentage of the total area of the rectangle. And so that will give us a pretty good idea of our target. All right, so let's go ahead and go over into Octave or MATLAB. I'm going to use Octave for this video and build up a simulation here. So the first thing that we always want to do, of course, is to just put in here, put in your name and the date, and some comments describing what we're going to do. And then, of course, we want to make sure that we're starting off with everything cleared. So I'm going to clear the screen, I'm going to clear the variables, and I'm only going to use one figure, but I'm going to go ahead and make sure that I clear that figure to start. And I also have already kind of went in here and defined the maximum velocity, right? That's this peak, which I've already said we're going to go all the way up to 2.2 meters per second. So that's going to be the height of my rectangle. All right, so that's the height of the rectangle. And then I'm gonna build a matrix, which is going to look kind of like the rectangle here. So I'm going to build a random matrix, and so I'm going to have to put rows and columns in that. So what I'm doing here, I'm just going to start off with 10 rows, and I'm going to make it a square matrix so that I have the exact same number of columns as I do rows. And then I'm going to go through here, and just to kind of start off, I'm going to build my random matrix, which I'm just going to use a generic term A for my random matrix, and I'm going to use the rand function, and it's going to be size rows comma columns. And this way I can increase how many darts I throw very, very quickly by just changing the number of rows. That'll change also the number of columns, and so every time, if I want to change that, I can just change it right here and generate that new number. I'm also going to go ahead and define my total, let's see, that my random function, or my random values though, remember the rand function only goes from 0 to 1. So the first thing I need to do is multiply that times the maximum velocity. And that'll give me the height going all the way up to the maximum value. So I'm going to go from 0, and I'm scaling 0 to 1 all the way up to 2.2. Okay, so you can't forget to scale our random values. Then I'm going to go ahead and calculate my total darts that I'm going to throw, which is going to be the rows times the columns. All right, so that's the total number of darts. And I just want to kind of take a look at this for right now. So I'm just going to plot, or well, I need to create a time reference also. So I've created my maximum velocity, which is the random value, or I set the maximum value here. So now what I'm going to do is I'm going to build my time vector, and the best way to do that is using the lens space. So I'm going to create my time vector here, t, which is going to be the lens space, and I like to use the columns. But I already said that the time is going to run from 1 to 7 seconds, and I'm going to match it to how many columns are in my matrix. So if you think about the matrix, you have rows. Okay, so we have rows of the matrix going this way, right? And the columns are going this way. So if you think the columns are kind of going along with time. So that's why I'm using columns for my time. All right, so I'm going to run and get a linear spacing between 1 second and 7 seconds for however many columns that I have. So currently I'm going to start off with only 10 columns, but I will change that as we run through the code. So now I can plot my matrix, and I just kind of want to look at it right now. So I'm going to plot the matrix A, and I'm going to, because these are darts, I'm going to kind of draw little triangles that'll look almost like an arrowhead or something. So I'm going to draw some triangles, and I'm not going to specify the color, and it'll just randomly select some colors for me because there's so many. And I'm just going to plot this, and then I'm going to go ahead and set my axis to be the minimum t. So it'll be min t to maximum t, and then 0 is the starting point, but max velocity, which is the 2.2. All right, but by using these variable values, if I decide to change them later, it'll automatically make the adjustments for me. All right, so it's nice to do that. All right, and I'm also going to add in one extra piece here. This is a function that I created called add plot box, which adds a square box around my plot, because for some reason my version of Octave isn't doing that automatically. Normally MATLAB will do that for you automatically, but my Octave version for some reason is acting weird, so I just added that. So here you can see our plot, and its time is starting at 1 second down here, and the velocity is 0, and we're running all the way over to 7 seconds, and the height is going up to 2.2 meters per second. All right, and then you can see all these little arrowheads or triangles in here showing you the matrix. Now you can actually see this is a random. Remember, this is actually in the linear. As we go across linear, it's not random, right? So it goes from 1 to 1.6, or well, actually 1.7 over to about 2.3 over to 3, and so on. So it's actually in the X direction, it's not random, but in the Y direction, it's definitely random. And so you can see there's some gaps in here in places, and other places are a little bit more clumped together. Like right here at about 4.3, you see this line here, there's one value way up here, all the other ones are falling way down here. But notice there's 10 of them. So if we start counting, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 triangles. So in every column, there's 10 triangles randomly dispersed throughout there. All right, so that is my um, that is what my A matrix looks like. Now, if I run this again, notice like the 4.3, you got a lot more of them are higher here because it's random. So every time you run this, your points are going to show up somewhere differently. All right, so I'm just going to come back over here now to the program, and I don't really need to plot this at this time here. I just wanted to show you what that looked like. So I'm going to run the axis way down here below because later on I'm going to want to reset those. But right now I want to create the function and plot the function. So if you look here, you see here's the line, right, is showing you, there's your line, and I want to plot that line so that we know where it's at. Okay, we don't really have to, but it just gives us a nice reference. But I want a nice smooth line, and right now I'm only doing 10 points, so that's kind of clumsy. So I'm going to create a smooth time vector. So I'm going to call this T smooth, which is going to run. I'm going to just use a regular linear. Well, we can even do a lens space if you want from 1 to 7. But this one I'm just going to hard code and say give me at least 200 points. All right. And then I'm going to create the line of my function, which, as I said before, is sine t times the cosine of 2 times t plus 1. All right. And so now I'm just going to plot t smooth comma y smooth, and I'm just going to plot that as a blue line just to have a nice plot. And that didn't run, so I have a typo somewhere. Let me look at the command window, and my vector lengths do not match. I think I forgot to use t smooth. Yeah, right here, when I evaluated the function, I need to use my T-smooth version. Okay, and so that I can get a smooth plot of 200 points. And so there you see, there is my function. It's running from 1 up to 7. It's got a maximum value at 2. And it's just a nice smooth curve there as a reference point. All right, so now I'm going to turn hold on so when I plot later, it'll remember that. And so now what we want to do is we want to start running through our matrix, right? So right now, remember, we have 100 darts in our matrix because it's 10 times 10. So there's, if you look at, well, I deleted that triangle or that plot, but if you looked at that plot, let me just run that on figure 2 so we can look at it. Figure 2, and I'm going to clear that. And then when I create this plot, I'm going to be on figure 2. And then I'm going to return to figure 1 for the rest of it. I guess it doesn't matter. I could have done 1 and then 2, but I want to be able to flip back to the raw triangle, and let's see, there was the plot right there for that, and I wanted that on figure 2. Okay, I got to have it after my t vector. Otherwise it wouldn't plot. So just as a reminder, so here is my matrix, and again it didn't draw the blocks, so I throw that add plot box in there just so it would be in there. But so there's my figure 1, here's my figure 2, which is just showing you all the triangles in there where we have the random values. So these are the random values in there, anywhere between 0 up here to the top triangle, which is at about 2.16, 2.19. It can't go above 2.2, right? Because that was with the max velocity. But notice, because I didn't set my axis this time, the vertical actually is going all the way up to 2.5. But that's just a reference plot. But I guess I'll set the axis on that, which I had way down here. I'll just copy this and paste it up here so that it gets set also. But then we're going to return to figure 1, and we'll be looking at, I'm on figure 1, I've already got the nice smooth, there it is, the nice smooth plot of the function. So now what we want to do is we're going to take our number of hits, we're going to set hits equal to 0. So we're going to initialize our hits to 0, and then we're going to run through each and every one of those triangles, right? We're going to run through each and every one of these triangles and see whether they're above or below the curve. And so the way we do that, we have both rows and columns, so I need 2 for loops. So for column, I'll use C as my variable from 1 to the total number of columns. And I like to throw in the end for there. And then we're going to do it for the rows also. And it really doesn't matter which one you do first, just as long as you do both, okay? So we're going to run for rows and columns. And what we're going to do here is we're going to evaluate at, for every point. Now remember, if we look at that plot, remember that the way I'm running this, actually they're all lined up at even times, okay? And so that makes it easy to evaluate the function for the columns. And so what we're going to do here is for each one of those triangles, we're going to evaluate the function, the actual velocity. So remember, the actual velocity is the sine, but now we're going to evaluate it at the time iteration right here for each column. Okay, so we have to do time at that t times the cosine of 2 times that c, or that time, plus 1. And so that's the actual velocity. And then we're going to look at the random velocity. Well, the random velocity, we already generated all these darts, right? This matrix up here is all those darts. So all I have to really do here is just say, give me A at this row and this column. And then, I really don't even have to separate it into a different variable, but it makes it a little easier to read. And now I'm going to say, if the random value of velocity is less than the actual velocity curve, then that is a hit. And so what I'm going to do is I'm going to do hits plus plus, which will add 1. Every time this random velocity is less than the actual, it's going to be a hit. And then on top of that, I'm going to go ahead and plot that hit. So I'm going to plot at time t for this column. I'm going to plot this random value of velocity, and this is a hit, so I'm going to plot this with a circle, a green circle, okay, to see that it's a hit. Now if it's not a hit, I don't need another if, because if it's not a hit, it's obviously a miss. And I don't need to count misses. You could if you wanted, but
You already know that because we already know how many total darts we have, and you're going to know how many hits you have. So if you needed to count misses, it would just be the difference. But so we don't need to count them, but I do want to plot the miss, okay, which is the random velocity, which is going to be above. And so I'm going to plot that as a red star up above. And I'm going to end my if. Okay, and I already have my hold on, and I've got my axes being set way down here. Probably got extra lines, probably didn't need quite so many there. But I have those down there. So now I'm going to run this. Now remember, we're only doing this for 10 rows and 10 columns, which gives me 100 darts. But what I want to do is I want to calculate the total area under the curve. So the total area underneath the curve is the total area times the hits divided by total darts. Okay, and you need to make sure I got my spelling correct. So that's my total area. Where was total darts? I did not calculate the total area, so let me calculate the total area. The total area which I need to put above, if I'm going to use it here, I need to make sure it's above. But the total area is the maximum velocity times the max t minus the min t. And so that'll give me my total area. And then the area under the curve is the total area times the hits divided by the total number of darts, which I do have calculated up here. All right, so then I'm just going to throw that in my title. Okay, so I'm going to use the sprintf to report all that information and just display it in the title at this moment, just to put it somewhere where we can see it after it runs. And so I'm just going to run this, and if everything worked, oh, got an error message here. End 4, I have a space in my end 4 there. Alright, so now you can see there is the blue wavy line, and it has a bunch of green circles below it, which are hits, and it has a bunch of red dots above, which are the misses. And you can see there's a lot of gaps in here, alright, but when you look at this, you see that the area under the curve it's calculating that to be 6.2 meters, and that's 47 out of 100 darts, or 47%. Alright, now the one thing I want to point to, if I rerun this, make no changes but rerun it, notice that the area under the curve is now 6.6, and I got 50 hits instead of 47 hits. That's the randomness of this. Every time, if you just rerun it, so if we just come back and rerun it without making any changes, we have a different, see, this time I only got 41 hits. Alright, and so the accuracy of this technique is not really that accurate, but you can improve the accuracy by throwing more darts to fill in these gaps where there's white space. And so right now I'm only doing 100 darts, and you saw I ran it 3 times and I got 3 completely, I mean, the answers went from 5.4 all the way to, what was it, 6.6? I don't remember already, but but if we come up here now and I change it, let's say, let's go from 20 to 30 rows, right? So I'm going to go from 100 darts, and it's taken a little while here. All right, so I went from 100 darts to 900 darts, but you see how long it took? All right, so by increasing that, boy, it took a lot longer. But you can see now it's given me a 6.2 value, 6.26, and if we run it again, without changing the value, if I just run it again, we see that it's taken a little while to run. And there it is, and now we have a 5.9 value. So we still got some gaps in here, but it's maybe getting a little bit closer, but still not all that much. Now, one thing we can do is there's built into the software is kind of a clock, right? I mean, computers have clocks built in. And so we can basically use the tick-tock of the clock to figure out how long this takes. So up at the very beginning, I'm going to run tick. And down here, I'm going to run talk. And what it's going to do then is display how long this took. And so if I run this and give it a few seconds here, it's thinking. But as I run this, you see that it ran, right? We had to wait for it. But if we come to the command window, we can see the elapsed time was 8 seconds. All right, so the elapsed time here, I'm just going to record this inside a comment in here. Elapsed time was 8.8 seconds for 900 darts. Okay, so for 900 darts, it was 8.8 seconds. All right, so now I'm going to come back up here and I'm going to change it to 50 darts. Well, that's 50, excuse me, it's 50 rows, so it's 2,500 darts. 50 rows, 50 columns, it's going to be 2,500. And so once this gets done running, we're going to see, right, we went up from 900 to 2,500 darts. And it's still thinking. All right, so we went from 900 darts to 2,500 darts. So now we're at 2,500 darts. Let's look at the elapsed time. Now the elapsed time, it's still running. It's not done running yet here. Okay, there, okay, that took 31 seconds. All right, so that took 31 seconds for 2,500 darts. And so now I want to run this one more time. Well, let's look at it when we look at our plot. Right? You see it's pretty good, but still there's a lot of white space in here. All right? So I'm going to run it one more time with 100 rows and 100 columns, which will be 10,000, which is what we were asked to do in the homework, is run it for 10,000. And so I'm going to run this, and I think I'll hit pause on the video to let it run, and then we'll look at the time. All right, so you can see that it's drawn a few points in there, but it's still okay. You can see it's done a partial drawing here, but it's not done drawing. Alright, so I've unpaused the video here for a little bit just to let you know that, you know, it's still running. It did an initial drawing here of the first two columns, and you can see all those different points, but it's still thinking, it's still going here. And remember, we've got the talk, so we'll see the elapsed time when it's done. Alright, well, I'm still waiting on this to run here. I don't even know how long it's been now, but it's still running. But I did want to pop over to figure 2 and just show you now, right? We're doing 10,000 darts. And so within this rectangle, we're effectively throwing 10,000 darts. And as you can see, we're getting a pretty good coverage throughout the entire rectangle. So it's still running through and trying to plot 10,000 dots over here onto figure 1. Now look there, you can see that it just popped up the screen, it refreshed the screen, but it's only up to a little bit beyond 6 seconds, so it's still got a ways to run here before it hits the 7 seconds. So I'll pause it here, we'll give it a little bit of time yet. Alright, so I did want to point out to you, right, it hasn't updated since what you saw before here. It's still got a little bit of, you know, about 2/3 of a second in the simulation to calculate yet. And what's really taken all the time is the plot. So at this point you can see the red is going all the way up here to just about 2.2. That's the max that it can go. And like this value right here looks about maybe the highest at 2.19. And there it is, there's finished plotting there. And you can see that that was 10,000 points, or 10,000 darts, and it came up with a value of about 6.1. But this flipped back over to our command window. Maybe it looks like it's not quite done. There it is. That took 10,000 points, took over 315 seconds, right? So 5.2 minutes. Okay, so it took 5.2 minutes to do those. Okay, so I'm just going to throw that in here as a reference. All right, so the elapsed time for 10,000 darts was over 5.2 minutes. So now you know how long I was waiting. And there's 5.2 minutes it took to run those 10,000 darts. However, I want to point out that the problem, why it took so long, wasn't to calculate the area under the curve, but to plot each point. Because when you look at all these points on here, back to figure 1, when you look at all these points, I'm plotting one point at a time. So when I put on, you know, I drew the line first, I drew the line, and then I started, and that was 200 points to get that smooth line. But then I started plotting the reds and the greens. And every time, the problem is every time I add one more green circle or one more green or red star, one more red star, it's got to redraw everything all over again. And so that's what takes time, especially as we end up getting more and more. It's got to come back and redraw everything every time. So it's really, really slow the way I did it, because every time I find a hit, I plot the green circle, and if I find a miss, I plot the red star. And that's just not very efficient. So really what we want to do is store the X and Y value for every hit and the X and Y value for every miss. I want to just store those and then plot them in groups. So I'm going to plot all the hits at one time. And that way I don't have to redraw the graph 10,000 times, which is what is truly taking the time. So I'll show you this here. Alright, so the first thing we need to do is I'm going to generate some null values. Let me show you this in the command window here. So I'm going to save all the point X values and Y values that are hits. So I'm going to create this variable called X hits equal to nothing. Alright, and the way I do nothing is I just do the two brackets with nothing in between them. So this is This is creating the variable, but not putting anything in it. Now, as I want to add something to it, let's say that my first hit is at, remember actually the X is in time, so it would be like, say, 1 second. So I could say the first hit was at 1 second, but I need to remember all my other hits. And so the very first time there's nothing in there, but I'm going to add 1 second to it. All right, and then the next time I have a hit, let's say that was at 1.7 seconds. All right, and I'm sorry, I missed an S in here. Okay, so let me start this over. So I'm going to initialize it to nothing, and then the first time it's a 1, but I forgot to put the S right there. So let me add that. Now the next time it's a 1.7, and the next time it's a 2.3, and you can see that I can't just keep adding and adding. So I'm basically saving up all the X and Y values for my points in a vector, and then I'm going to plot all the hits in one step instead of plotting. How many hits did we have over there? Let me look. Right, I had 4,624 hits. So instead of plotting that thing 4,600 times for all the hits and over 5,000 times for the misses, I'm going to store those values and then plot them once. All right, so let me get back to the octave screen and the editor. And so what I'm going to do is I'm going to take these plots and move them down here. And I'm going to have to edit them once I create my variables. So I'm going to create these null variables right here. Outside the loop, I'm just going to initialize. Outside the loop, I'm going to initialize this X hits and Y hits. And then I'm going to store, if it's a hit, I'm going to store the X and Y for plotting later. And if it's a miss, I'm going to store the time, which is the X, right? What time is in the horizontal or the X direction of the plot, and Y is the velocity point, and I'm going to store those. So I'm going to store the hits, and I'm going to store the misses, and then down here, after I've evaluated whether it's a hit or a miss, now I'm going to plot all the hits. And make them green O's. And then I'm going to plot all the misses. And make those red stars. And so now I'm going to run this. Boom, it's done. All right, and so you can see there it ran. This time it actually had almost 4,600 hits, just 3 shy of 4,600 hits. But what I want to show you here is the time it took, 1.5 seconds. That was still 10,000 points. Okay, so for 10,000 points, or 10,000 darts, but I stored the points and plotted later. Alright, so it went down from 5.2 minutes to under 2 seconds. Alright, so it's that plotting that was taking all the time. So if we just do a little bit more coding and capture the points and then plot the points in groups, the savings is tremendous because it's the plotting. Plotting takes more time than practically anything else. And so if you spend a little extra coding time to store your points and then plot your points later, you can tremendously save time, right? From 5.2 minutes all the way down to 1.58 seconds. Let me just run it one more time. Boom. Done. There it is. And look at the time again. 1.518. The other time was 1.586. All right, so one more time just to say best out of three. All right, and look at that time. 1.5 or 1.497, so under 1.5 seconds. So this was 1.6 seconds. So, but when I ran it, plotting each individual point, it took 5 minutes. So, like I say, spend a little extra time coding, you can save a lot of execution time.